to the day 3 of first week of this course. So, in the last 2 classes we have looked into various different applications that are possible with laser, and also we looked into the brief history of laser development. So, with this brief background, we can now go on to learn about the basics of laser, the laser action. Okay. So, in the previous class I mentioned the full form of laser, that is light amplification by stimulated emission of radiation is the full form of laser. And we said that there are few things that we need to know in order to understand the laser, how laser works, what is the basic principle of laser. And one of the most important thing to learn will be the stimulated emission of radiation. Now, before we can start talking about stimulated emission of radiation, we should know what are the different processes that can take place when light interact with matter. So, as we know that light can absorb or emit. Okay. So, how exactly this absorption or emission process is? So, in a word, what are the optical transitions that are possible, okay, within a system which can be an atom or an ion or molecule or large material. So, we will start with a simple description of optical transition in an atom. Okay. There are some benefit of using an atom to describe this process, because this is very simple. We do not have to consider any rotation or vibration of an atom, okay, but we can deal with the simple energy level of an atom. So, we will start with a very a simple energy level diagram, which is known as a two-state model or two-level system. So, we will consider two-level system. So, what is a two-level system? A two-level system consists of a ground state and an excited state. Okay. So, we can write the ground state and excited state by giving them the names state 1 and state 2. So, the electrons in an atom can reside in ground state. Now, what happens when we shine light into this system consisting of two states? And also one more thing I need to specify here, that the energies of the two states are given by E1 and E2. Now, if I shine light such that the frequency of that light, let me call it as 1 2, nu 1 2, such that h nu 1 2, where h is the Planck constant, is equal to the energy gap in this system, that is E2 minus E1. Okay. So, I am bringing a light with a frequency nu 1 2 such that the h nu 1 2 matches the gap between the energy levels 1 and 2. So, what will happen? This atom will be now excited. So, this from the ground state, it will make a transition to this place now. So, this process is known as absorption of light, or in short we call it absorption. So when we let this process happen, what do I observe? So in other word, what is the observable? So if I come with a light, I can detect the light in absence and in presence of this system, this two-level system. So the intensity of the light in absence and presence of this two-level system, if I look at, then what will I see? If I see or measure the intensity of light, then when this process happens, I will see a sudden drop in the intensity, and this drop is due to the process absorption. Okay? So I can come with a different frequency of light. Whenever the frequency matches with this gap, I can see this. So if I plot it against nu, I see a plot like that. So this is my observable. Okay. So many of you are probably aware of this fact. So once I take the system from ground state to the excited state, the molecule will be there. Now for how long? Will it be there forever, or it will be there for a certain period of time? The answer is that this state of the system, that is when the molecule has made a transition from here and is residing on this state 2, it will not be there eternally. It has a finite time for staying in that particular state 2, which is known as the lifetime. Okay. And so this state is associated with lifetime, which is normally denoted by this tau. Okay. So this tau amount of time is the maximum amount of time for which the molecule can, or atom can, stay here at level 2. After this time tau, the molecule is going to jump back to the ground state, that is state 1. So what will happen if I can show here, or say I will use the same diagram. So after some time, when or maybe I can go for separate one so that it is easy for you to understand. So all the description remain as it is. Only thing is that now molecule is here and I am not doing anything. I am not perturbing anything, perturbing the system with any external force. So on its own, it will make a jump from this state to this state after a time period tau, which is the lifetime of the state. And when it jumps from state 2 to state 1, what will happen? The energy equal to the gap E2 minus E1 will be emitted. So accompanied by this jump, there will be a release of photon, and that photon frequency will be such that it matches this gap. So again the photon frequency will be nu 1 2. You may call this as nu 2 1, but you can understand for this given two level system, it does not matter whether I write nu 1 2 or nu 2 1, because both are same. So we will all the time use this nu 1 2. Okay. So the first process was absorption, and this process is known as, of course, emission, because a photon is being emitted. Now what kind of emission? we are not perturbing the system externally, so it is happening spontaneously, and therefore this is known as spontaneous emission. So these are the two processes that people knew for a long time, okay, that this is what happens. Now if we want to understand the these transitions in a detailed way, and for that matter if we want to really understand how laser works, we need to understand these processes in terms of their rate. So we need to know the rates of this optical transition. Any given optical transition, we need to know at which rate this transition is happening. Then we will be able to understand this processes a bit more, and also we will be in a condition where we can manipulate this transition so that we can get something useful, something like laser. Okay, we will learn that in a bit. So if we look at the rate for this process, then what I can say that before doing that we need to define some more things, that is the population. So the population of atoms in state 1 and state 2. So if I say N1 is the population of ground state 1 and N2 is the population of state 2. Now the rate, so rate of absorption, let us consider that first. What is the rate of absorption? So I can understand the rate of absorption by noticing the rate at which the number of atoms residing in state A deplete with time. So rate of absorption is equal to the decay of number of atoms at 1. So it is minus dN1 dt. This is my rate of absorption. Now how can I find the rate of absorption? Then if we need to find that out, then what we have to do, we have to understand on what thing this rate of absorption actually depend, or the decay of population in the ground state, state 1 decays. So this rate of absorption is proportional to the number of atoms itself in that particular state. So in our case, rate of absorption is proportional to N1. More the number of atoms in that level, more will be the optical transition, that the rate will be more. And what will be the second thing that it can depend on? If you think about it, it will depend on the density of photons with energy nu 1 2 that is available. So more number of photons that are available to make this transition, the rate of transition will be more. So minus dN1 dt is proportional to the density of photons having frequency nu 1 2, and let me call this as h nu 1 2. So rho is the density of photons having frequency nu 1 2, and we write it in this fashion, okay, rho of h nu 1 2. So if I put together, so this one let me write down, this is density of photons having frequency nu 1 2. All right. So, if I have to find out the what is the value of minus dn1 dt, then we have to go from this proportionality to an equality condition. So, if I can write that up here, let me take the liberty to erase this part. So, from here I can write this rate of absorption equals to again minus dn1 dt equal to some constant. Let me call that constant as B12 and multiplied by N12, sorry, N1 and rho H nu 12. So, this is my rate of absorption. Fine, we got what is the rate of absorption. Now, let us find out what is the rate of spontaneous emission. Okay. So, here we have the picture for spontaneous emission. So, we have to find out the rate of spontaneous emission. Okay. Let me put it in this way. So, this one I can write in a differential form as minus dn2 dt in a very similar way as we have done it for absorption. In absorption, we dealt with the ground state, change of population of the ground state, and here for spontaneous emission we are dealing with the change of population of the excited state, that is state 2. So, the number of atoms in state 2 is N2. So, the change in N2 with time is my rate of spontaneous emission. Okay. And remember, here there is no light, there is no spectral field or radiation field present when I am considering a spontaneous emission. So, here what are the things that this minus dn to dt will depend on? So, it will depend on only one thing, that is the number of atoms present in state 2. Okay. Since we do not have any radiation field here for spontaneous emission, so this is the only thing that it can depend on, unlike the case of absorption where it depends also on the radiation field. So, I can go from this proportionality to the equality by putting some constant and let us call it A21 multiplied by N2. So, if you see the notations that we are using all the time, it denotes from which state to which state. Okay. So, if you are looking at A21, you would be able to tell that it is a process involving a transition from state 2 to state 1. Okay. And you have the corresponding N2, which is the population at state 2. On the other hand, if you look at for the absorption process, you will see this is from 1 to 2 and it is also associated with the number of atoms in the state 1. So, it is very easy to figure out. Okay. So, I have got my rate of spontaneous emission. Okay. So, at this point let's talk about a bit of work done by Max Planck. In the second class, we talked about the history of laser development, and there we mentioned that it won't be possible to go ahead and develop laser until unless there were a tremendous theoretical work done by two scientists Max Planck and Albert Einstein. So let's start with what did Max Planck do. So there was an existing problem of black body radiation. Okay, so most of you have learned about black body radiation in your high school physics, or at least in the in your undergrad days. So a black body, it emits light, correct? Now there were certain issues regarding the spectra of a black body, a perfect black body. So people were trying to explain the spectral behavior of black body, and there were a lot of difficulties. Okay, even if you can explain it to the most extent, but when you go toward the UV region of the spectrum, one could not explain, and Max Planck was trying to do that. In order to do so, what he did, he proved that the optical transition that we see, which results in having a spectrum, is not discrete, okay, is not continuous, I am sorry, rather it is discrete. So he proposed this discretization of optical transition, and he proposed the transition to be quantized. So quantization of optical transition came from Planck's work, Max Planck's work. And in this work done around 1900, he ultimately got a relation which is known as Planck's law, where he gave us the expression for spectral density. So is the radiation density, which is a function of frequency and also a temperature. So why is it so? Because when you work with black body, you take it to be in thermal equilibrium at a particular temperature T, and then you deal with its spectral property. Okay, so at a given temperature, the spectral density that is coming out of a black body, okay, and for a given frequency that you are looking at, this is the spectral density, and this is given by H So Planck gave this formulation where rho is equals to 2h nu cube into c by c square multiplied by this quantity. All right. So what are these terms? H is Planck constant, nu is the frequency of the light that we are considering, c is the speed of light, okay. So and k is the Boltzmann constant. So this is and capital T is the temperature. So you pretty much know what are the different quantities on the right side of this. So he did it, and this could explain the black body radiation to a quite good extent, okay, at that point of time. Now let's come back to our earlier discussion of this optical transition. Okay, we will need to use this in a very after a while. So after Planck did this work, Einstein was trying to explain also the black body radiation problem by treating the black body to be a unit which is consisted of several number of such oscillators. So this two-level system, we can call it as an oscillator. So the atoms can go here to here, here to here, and absorb or emit photon. So these kind of simple two-level oscillators, Einstein took it as a unit that form the overall blackbody radiation. So there are n numbers of such oscillators constitute the whole blackbody radiation. So what he was trying to do ultimately, that treating blackbody in this way, he should come to the same expression that Planck has got, right? So Albert Einstein he was trying to come to the expression of Planck for this spectral density. He was not successful in doing so. Okay, so there were certain problems associated with this one. So what we will do, we will stop here today, and in the next class we will start looking at how actually Einstein solved this problem and go to the same form of Planck's expression, Planck's law, by treating the blackbody as an ensemble of this kind of two-level oscillators. So see you tomorrow again. Thank you very much.